Hi guys, in today's video we're going to talk about the fundamental theorem of calculus. In the study of calculus, the fundamental theorem is the most important idea as it connects integration and differentiation together as opposite processes to one another. The first part of the fundamental theorem states that if we define a function capital F of x as the area under the function f of t from a to x, then the derivative of fx is simply the function at x. The second part of the fundamental theorem leads directly from the first, and it states that the definite integral from a to b of any function f of x is equal to the value of the antiderivative of that function at b minus the value of the antiderivative at a. This second part is particularly important because it gives us a way to calculate areas under curves over a certain interval to be calculated algebraically instead of using the numerical methods that we've been using so far. We'll take a look now at where these two come from and how to understand them. To start, let's imagine that we've got some function f of t, and this function is continuous over the interval a to b. We now imagine a point x that lies within the interval a to b. We're now going to define a function that tells us the area under the curve from a to the point x. Our function capital F of x, then, is the integral from a to x of the function f of t dt. If we take the derivative now of both sides of this equation, we get that d dx of f of x is equal to d dx of the integral from a to x of f of t dt. Looking at the area that we've defined from a to x, the derivative of that area as x changes from x to x plus h is simply going to be determined by the height of the function at that point. If the function is high, then changing from x to some small increment above will add a large amount of area. If the function is small, then only a small amount of area is going to be gained. So the derivative at this point of the integral from a to x f of t dt is simply the value of the function at the point x. Now this is really important because what we're saying is that f, our capital F, dash x is equal to f of x. What this means is that the area under the curve from a to x is an antiderivative of the function itself. In this way, we finally can define integration and differentiation as opposite processes to one another. This result is also really important in calculus because it implies that every function that is continuous over an interval has an antiderivative. We'll take a look at this result again in a slightly different way. So here we've got a function drawn, f of x, and we're taking the area from some point, in this case 0, up until some value x. And we're defining that by a function a of x, the area under that curve from 0 to x. If we take a second value some short distance away, h, the area there is obviously a of x plus h. And the difference between those two functions is just this area in here. Now, we can estimate that area in two ways, as we've seen. We could use a left rectangle, or we could use a right rectangle. And we're going to use the fact that these two areas will under and overestimate the area to put limits on the value of this difference. So obviously in the case of left rectangles, we're going to get an underestimate in this case, and our area estimate is going to be the function at x multiplied by the width of the rectangle. And using right rectangles, we can get an upper limit because it will give us an overestimate. We use the function at x plus h and multiply by h. We know that the true value for that extra bit of area added on lies between these two boundary values. We can divide through by h to get that the function at x must be less than or equal to a of x plus h minus a of x over h, which is then less than or equal to the function at x plus h. The problem is that the limit as h approaches 0 of f of x plus h equals f of x. Meaning, as we take these 2 points closer and closer together, the two boundary values become equal. F of x is equal to f of x plus h in the limit that h becomes infinitesimally small. So if the two boundary values are becoming equal in that limit, then what that means is we can state that the limit as h approaches 0 of f of x is equal to the limit as h approaches 0 of a x plus h minus a of x on h. And we'll notice, of course, that that is exactly our definition of the derivative of a of x. Therefore, f of x in this case, as the limit as h approaches 0 doesn't affect f of x at all, is equal to a dash x. What we've proven here is that the area function is an antiderivative of the function itself, because a dash x only gives f of x if a of x is an antiderivative of f of x. Starting with the result of the first fundamental theorem, that capital F of x is equal to the area under the curve f of t from a to x, we can now take a look at how to work out the area under a curve between any 2 points. So we have the integral from a to b of a function f of x dx. We can rewrite this as the difference between the areas from c to b of f of x dx and c to a of f of x dx. We can look at this same statement graphically as the total area from a to b would be equal to the area from some point c to b minus the area from c to a. The result of this is that the area under the curve f of x from a to b is equal to the value of the antiderivative function at b minus the antiderivative function at a. Now, of course, we know that antiderivative functions are actually an infinite number of functions, f of x plus c. The value of c is determined by our little c that we chose, where we're taking these areas from. Obviously, if I take a slightly later value, then the total areas that I measure from c to b and c to a will be smaller. If I put c earlier, those areas would be larger. It's irrelevant, though, exactly which value of c is chosen. It doesn't play a part in the final answer, because no matter where c is positioned, the area from c to b includes the area from c to a, and we subtract that away. In this way, you can use any antiderivative function of f of x. So what's normally done is we set the constant that we get when we take the antiderivative to 0. We ignore it completely. So the last step now is to take a look at an example. We want to know the area under the curve 2x plus 1 between the values 2 and 5. In this case, our function f of x is 2x plus 1, and an antiderivative function for f of x is x squared plus x. Again, the antiderivative could have had any constant value on the end, plus 2, minus 3, plus 1.475. But as we're going to find the difference between this function at different values of x, that constant is always going to cancel itself. So we just take the antiderivative function with c equal to 0. In our next line of working, we put the antiderivative function and we state the limits that we are going to calculate it between. This notation, when we place the antiderivative inside square brackets with the two limits indicated, is used as a shorthand to represent evaluating the function at b and then subtracting the evaluation of that function at a. So substituting the values 5 and 2 into our antiderivative x squared plus x gives us 5 squared plus 5 minus 2 squared plus 2. This then equals 30 minus 6, which gives us that the area under the curve 2x plus 1 between 2 and 5 is equal to 24.